In this video, we're going to start looking at probability, first introducing some basic terms and some just basic concepts of probability. So we're going to learn the basic terminology of probability theory, be able to calculate simple probabilities, and actually we are not going to do this last thing, so just those two things. So some definitions. An experiment is a process by which an observation or outcome is obtained. The sample space is the set S of all possible outcomes of an experiment. And an event is any subset E of the sample space S. So let's say those things again. We're going to be talking about an experiment. An experiment is going to be anything that we can observe an outcome of that. We're going to be talking about rolling die, flipping coins, but they can get into any more kinds of things as well. Again, so an experiment has things we can observe. Those things we can observe are called outcomes. All possible outcomes of an experiment is a set, and we're going to use all of our knowledge about set theory from the previous unit in this unit as well. The sample space is all possible outcomes, and if we look at any subset of that sample space, that is called an event. So to look at this in a real-life sense, let's consider the experiment of rolling a fair six-sided die. So the possible outcomes of that experiment are that you roll a 1, a 2, a 3, a 4, a 5, or a 6. So this set, 1, 2, 3, 4, 5, 6, is our sample space, the set of all possible outcomes. Then let's look at some possible events. These are subsets of the sample space. So E1, an event, we'll call the set 3, is the event that we roll a 3. E2 is the event 2, 4, 6. That is that we roll an even number, 2, 4, or 6. Doesn't mean that we roll all of them at the same time. It's just one of those things will happen. E3 is 1, 2, 3, 4, 5, 6. That is a subset. It's an improper subset. This is just S. This is that we roll a number 1 through 6. Then we have a weird one. E4 is the set 7. This is that we roll a 7. And the last two sets give us two kind of weird sort of events that we have. A certain event is an event that is guaranteed to happen. It's a subset of S that's guaranteed to happen. That means that it's equal to the entire sample space. So this E3 here was a certain event. It is certain, it is guaranteed that you will roll a 1, 2, 3, 4, 5, or 6. Contrastingly, an impossible event is an event that cannot happen. It's an event that's equal to the empty set, or it's just not a subset of S. So here, rolling a 7 on a six-sided die, that is an impossible event if we're just rolling one die once. All right, so the experiment is anything that we can observe an outcome. All of those outcomes we can observe are the sample space. Any subset of the sample space is an event. And now we can start looking at probability. The probability of any event occurring is the likelihood that that event will occur. We denote the probability P of E, and the probability of E is given as P of E equals the size of the set, right? This is the size of E over the size of S. That's the number of elements in E over the number of elements in S. And this is true if the experiment's outcomes are equally likely. So rolling a die, all of those outcomes are equally likely. It's a fair die. And we'll look into problems where it's not equally likely, but it won't be in this video. We'll look at it a little bit later. So we have the number of elements of S. This is our total number of possibilities. That's our denominator. And our numerator is the number of possibilities within that event. Similarly, but differently, we have this idea of the odds. So the odds in favor of an event are the number of ways an event can occur compared to the number of ways the event can fail to occur. And we denote the odds with O of E. And we're given the odds of E are going to be the size of the set E, the number of elements in E, compared to the number of elements in the complement of E. So N of E compared to N of E complement. So odds and probability are very closely related, and you should be able to translate between probability and odds back and forth. And we'll do that in a little bit. But they are different things, and they do measure different things. So let's look at an example to kind of help with this. A coin is flipped. We're going to try to find the following things. So first of all, the sample space. What are all the possible things that could happen when you flip a coin? Well, we know that we could either get a heads or a tails. You can try to get fancy and talk about how there's a third probability that it lands on its edge or something, but we're going to just ignore that part at the moment. The probability of an event we'll call E1 getting heads, well, that's going to be, so E1 is the set just H, that you get a heads. And the probability of that is going to be the size of E1 over the size of S. This is probably too much work to show here. The size of E1 is 1. There's one thing in there. There's two things in the sample space. So we have 50%, right? This is 1/2. This is 0.5. This is 50%. All of those things are the same thing. The odds of event E1, right? The odds of E1, that's going to be the size of E1 compared to the size of E1 complement. It's the number of ways that E1 can occur, that's 1, and the number of ways that it fails to occur, that is getting a tails. So 1 to 1 are the odds. You have an equal chance of winning and losing in that, or if this were a game or something, but an equal chance of getting heads compared to tails. The probability of event E2 getting heads or tails, so E2 is that you get a heads or a tails. We could think about this as H union T, something like that, right? We can just think about just H and T as well. So the probability of this, we're going to do this formula again, N of E2 over N of S. But what we're really looking for is the total number of possibilities, which is 2. And if you can either get a heads or a tails, then that's saying that we have 2 possibilities over 2. So this is equal to 1 or 100%. Same thing. That is a certain event. So the odds of E2 are the number of ways that E2 will occur compared to the ways that it won't. And this is going to be 2 to 0. All right, and that can be reduced to just 1 to 0 as well, but just 2 to 0. We'll talk about that with a different problem. So that's a certain event. Let's talk about an impossible event. How about we call E3 is the event that we get heads and tails. Well, we're just flipping one coin once. We can't get heads and tails at the same time. So the probability of E3 is 0 over 2, 0 or 0%. And the odds of that are going to be 0 to 2. All right, so probability and odds are closely related, but they're a little bit different. We can calculate them in different ways. Let's do another example, this time with a six-sided die. So we're just rolling the six-sided die once. This sample space here, S, is going to be our possible rolls on the die. 1, 2, 3, 4, 5, and 6. Now let's find the event rolling a 5. And we'll call this event E1. And that event is just the set 5. That is rolling a 5. That is the event E1. The probability of that, we'll go a little bit quicker here with the probabilities, is going to be the total number of options, 6, and the number of options that have rolling a 5, that is 1/6. And we'll just leave it at that. All right, the odds of rolling a 5 are going to be the number of ways that it can occur, 1, and the number of ways that it won't occur, 5. That is getting a 1, or getting a 1, 2, 3, 4, or 6. There's 5 ways that could occur. So this is 1 to 5, success to failure. The probability of rolling a number below 5, let's look at that event. We'll call that E2. That's the set 1, 2, 3, 4. That's the numbers below 5. And the probability of that event will be the number of ways it can occur over the total number of possibilities. And we can reduce that to 2/3, 4/6. So the odds here are going to be, there's 4 ways it can occur, 2 ways that it may not occur, 1, 2, 3, 4 compared to 5, 6. And we can reduce that to 2 to 1, kind of like a fraction. For every 2 ways it can occur, there's 1 that it may not occur. That's what it's saying. And when we're talking about large sample spaces, it doesn't really make sense to talk about not reducing these things. We want to have it in the lowest possibility, the lowest terms. So everything we've talked about so far has been about a theoretical probability. Given some kind of experiment, we can theorize that the probability of something will happen will be this. However, sometimes it makes more sense to deal with probabilities empirically, that is, looking at the actual data or the evidence. So let's look at some examples where that might be the case. So here is a baseball kind of thing. We have 8,389 times at bat. Babe Ruth, famous slugger, had 2,875 hits. So he went to bat 8,000 or so times, and 2,875 of those he hit the ball. And this stat that you can calculate from that is called the batting average. It is the number of hits over the number of at-bats. That is 2,875 over 8,389. And that gives a batting average of 0.343. So this is a empirical probability. This is called a relative frequency, or empirical probability. It's not theoretical, it's just based on some evidence that we have. Right, and we could say that we could expect Babe Ruth to get a hit about 34.3% of the time. That's how we could look at that relative frequency in real life terms. So note that with this example, there's no way that we could have done a theoretical probability. We needed the data to help us get that relative frequency. Note that's the exact same thing as saying an empirical probability using the evidence. And this is actually related to what we did in the very first video of this course, deductive versus inductive reasoning. Do we use the theory first to get a probability? Or do we use the evidence and then say something about the theory? We go from general to specific or specific to general. All right, another example of this, we can look at both empirical and theoretical. So during an experiment, out of 8 flips of a coin, only 1 was heads. So this is somebody sat down and flipped a coin 8 times and counted how many heads there were, and there was only 1. So we'll call the event getting the heads, we'll call that E. And note that the probability of E is 1/2. The probability of getting a heads is 1/2. We talked about that before. That's theoretical. The relative frequency, however, is going to be the number of times the outcome occurs over the total number of repetitions. So here there were 8 repetitions total, and only 1 time we got the heads, so that is 1/8. And note that 1/8 and 1/2 are not the same. We should expect, given our theoretical probability, that we would get 4 heads. We should expect 4 heads out of 8, but we only got 1. So thinking about that some more, this is what we call, or getting into the law of large numbers. And that is, if you would repeat that experiment a large number of times, that relative frequency of an outcome will tend to be closer to the probability of that outcome. So if you increase the number of repetitions, the empirical or the relative frequency will start to approach or get closer and closer to the actual theoretical probability. And that's the case even if they're never the same. So for instance, if you just flip a coin twice, it's really not that unheard of to think that you would never get a head in 2 coin flips. In fact, there's a 25% chance that would happen. So here the relative frequency of getting a heads to the total number of options is 0/2, 0. But you wouldn't just say just because you flipped it twice that you should have a 0% chance of getting a heads. It's just because we have a small number. When we do 8 flips, maybe we get 1 heads. Relative frequency is 1/8, that's 0.125, 12.5% of the time. If we start increasing the number of flips, so maybe you got 100 flips of a coin, 47 of them were heads, and the relative frequency would then be 47/100 or 47%. And then if we really increase the number of flips of a coin, let's say 24,000, 12,012 of them were heads. It's not exactly half, but it's close to it, and the relative frequency would be very close to 0.5, which we would expect. And this is the law of large numbers. If you keep on increasing the number of repetitions, you should get closer and closer to the probability, the theoretical probability. And that may not ever be the exact same thing, and depending on the experiment, it may be, close as relative as well. What does that actually mean? We can get into much more detail about what that means, but that's a more complex statistics course than talking about the central limit theorem. And we won't get into that in this course. Until the very end of it, we'll start scratching at it a little bit. All right, so relative frequency is very useful because it gives us actual data we can use, and we can maybe say something about the theoretical probability given that data. So let's look at another example. This one a little more complicated. A pair of coins is flipped. So now we're flipping 2 coins at one time. Find the sample space. So here, one option is that we get a heads on the first coin and a heads on the second coin. Another option is we get a heads on the first coin and a tails on the second coin. We could also get a tails on the first coin and a head on the second coin, or a tails and a tails. So here what we're saying here, let's say this one, this says a tails on the first coin, head on the second coin. That's our sample space. Note that we could actually find the size of the sample space using the fundamental principle of counting. There's two options for the first coin, and there's two options for the second coin. So you multiply them together, there's four options total. Just kind of looking back to the previous unit. So given our sample space, there's four different options what could happen. Find the event E that is getting exactly one heads. So E is the event that's a subspace or a subset of the sample space. And that's going to be exactly one heads, and there's two ways that could happen. A heads on the first coin or a heads on the second coin. So the probability of E is going to be, again, the size of E over the size of the sample space. There are four options total, and two of them have exactly one heads. So this is 1/2 or 50%. So what this last thing is saying, what's the law of large numbers? How can we interpret the probability of an event E? What is this trying to say? Is if we replicated this experiment a large number of times, we would expect about half of the results to have one head, exactly one head. Now, maybe with a large number of times, it's actually not that close to half, but if you kept on doing it more and more, you'd get close to 1/2. All right, so now this is introduced probability. In the next few videos, we're going to start getting into more and more complex things with probability and talking about much more complex problems. This is our base for the rest of this unit.